चलो हो गया लाइव ना। चलो ठीक है।
एक सेकंड चेक करता हूँ।
हो गया।
हाँ भाई लाइव है।
Over the last few years, AI systems have become astonishingly good at turning text prompts into videos. At the core of how these models operate is a deep connection to physics. This generation of image and video models works using a process known as diffusion, which is remarkably equivalent to the Brownian motion we see as particles diffuse, but with time run backwards and in high-dimensional space. As we'll see, this connection to physics is much more than a curiosity. We get real algorithms out of the physics that we can use to generate images and videos. And this perspective will also give us some really nice intuitions for how these models work in practice. But before we dive into this connection, let's get hands-on with a real diffusion model. While the best models are closed source, there are some compelling open source models. This video of an astronaut was generated by an open source model called WAN 2.1. We can add to our prompt and have our astronaut hold a flag, hold a laptop, or hold a meeting. If we cut down our prompt to just an astronaut, we get this. And if we cut down our prompt to nothing, we interestingly still get this video of a woman. If we dig into our WAN model's source code, we'll find that the video generation process begins with this call to a random number generator, creating a video where the pixel intensity values are chosen randomly. Here's what it looks like. From here, this pure noise video is passed into a transformer. This is the same type of AI model used by large language models like ChatGPT. But instead of outputting text, this transformer outputs another video that now looks like this. Still mostly noise, but with some hints of structure. This new video is added to our pure noise video and then passed back into the model again, producing a third video that looks like this. This process is repeated again and again. Here's what the video looks like after 5 iterations, 10, 20, 30, 40, and finally 50. Step by step, our transformer shapes pure noise into incredibly realistic video. But what exactly is the connection to Brownian motion here? And how is our model able to use text inputs so expressively to shape noise into what our prompt describes? In this video, we'll unpack diffusion models in 3 parts. First, we'll look at a 2021 OpenAI paper and model called CLIP. As we'll see, CLIP is really 2 models, a language model and a vision model, that are trained using a clever learning objective that allows them to learn this really powerful shared space between words and pictures. Experimenting with this space will help us get a feel for the high-dimensional spaces that diffusion models operate in. But learning a shared representation is not enough to generate images. From here, we'll look at the diffusion process itself. At a high level, diffusion models are trained to remove noise from images or videos. However, if you dig into the landmark papers in the field, you'll find that this naive understanding of diffusion really doesn't.
क्या है भाई?
अभी ये जो इनिशियली रैंडम नंबर से वो स्टार्ट किया है कोड में, तो उसके बाद जब वो इटरेट करके वो घोड़ा वाला जब इमेज बन रहा है, तो उसके ड्यूरेशन में कुछ भी प्रॉम्प्ट नहीं दिया गया है।
एरर से ही ना वो सीख रहा है। वो एरर को कम कर रहा है, ग्रेडियंट डिसेंट लगा रहा होगा और क्या लगा रहा होगा, समझ रहे हो तुम? ये दिख रहा है यहाँ पे, ई दिख रहा है यहाँ पे, ई तो यहाँ पे एरर ही कम किया जा रहा है और क्या कम किया जा रहा है। तो कोई भी मॉडल उसी तरह सीखता है ना कि
नहीं
उसको रियल आउट।
मैं ये पूछ रहा हूँ जैसे कि वो इनिशियली एक नॉइज इमेज है, उसको फाइन ट्यून कर रहे हैं, तो फाइन ट्यून के प्रोसेस में कुछ कॉन्टेक्स्ट हम लोग दे रहे हैं कि नहीं?
अरे देख, उसको पता है क्या कर रहे हैं? उस तो ऐसा कोई बच्चा है जिसको तू बताए कि नहीं भाई ये घोड़ा है, ठीक है, और तू उसको ये ना बताए कि ये घोड़ा है, मतलब ऐसा कभी सुना है कि तू उसको बताए भी ना घोड़ा है, अपने आप समझ जाए, ऐसा कभी हुआ है?
नहीं।
तो बताना पड़ेगा ना एआई को भी। तो मेरे को लगता है यहाँ भी यही हो
हाँ।
रहा है कि एआई को पहले ही पता है कि इमेज फाइनल आउटपुट दिखता कैसा है। वो बस
अच्छा।
अपने पैरामीटर्स को ट्रेन कर रहा है उस फाइनल आउटपुट तक पहुंचने के लिए। ऐसा वो बार बार करता है, तो उसके पैरामीटर्स कोई भी अपना रैंडम वीडियो भी कोई मतलब कि जो हम लोग काम के लिए भी बना सकते हैं, समझ रहा है तू?
समझ गया।
जो रैंडम नंबर वो जनरेट कर रहा है ना, अब जैसे कि मैं कोई रैंडम पिक्चर जनरेट किया, ठीक है, अब अब वो
हाँ।
रैंडम पिक्चर और जो रियल पिक्चर, जो आउटपुट का पिक्चर है, उसमें बस एक ही अंतर है, द अरेंजमेंट ऑफ पिक्सल्स।
अच्छा।
तो अरेंजमेंट
हम्म
ऑफ पिक्सल्स हर इटरेशन के बाद चेंज होता है।
हम्म।
लेकिन यहाँ पे शायद गेम जो है वो रैंडम नंबर जनरेट कैसे हो रहा है उसका भी है शायद। शायद उसका भी है ये गेम। बाप रे क्या है ये सच में। तो भाई सच में यार, आइंस्टाइन को मेरे को तो लग रहा है कि 2002 क्या कहते हैं 2100 का भी उसी को पर्सन ऑफ द सेंचुरी का अवार्ड मिल जाएगा, हमको लग रहा है साला।
आइंस्टाइन को।
करे जो भी ये लोग कर रहा है,
हम्म
ब्राउनियन मोशन जो भी है,
हम्म।
किसका दिया हुआ है ये सब?
ब्राउन ने मुझे आइंस्टाइन दिया।
हाँ, और कौन दिया है? ये
हाँ।
राम, पता नहीं भाई। 1905 को तो ईयर ऑफ क्या कहते हैं, मतलब सबसे इम्पोर्टेंट ईयर घोषित कर दो भाई फिर तो। फोटो इलेक्ट्रिक इफेक्ट दिया उस 1905 में, स्पेशल रिलेटिविटी दिया, ब्राउनियन मोशन दिया। ब्राउनियन मोशन लोगों को लगा उसमें बकवास है। अब जब स्किप टू 2025, ब्राउनियन मोशन सबसे इम्पोर्टेंट है। साला
चल।
क्या है भाई?
It doesn't hold up in practice. In this section, we'll dig into the connection between diffusion models and diffusion processes in physics. This connection will help us understand how these models really
अबे
work in practice.
रुकिए,
क्या हो गया?
ये पहले बता डिफ्यूजन मॉडल और एक क्या बोला है?
डिफ्यूजन प्रैक्टिसेस बोलना शायद।
In this section, we'll dig into the connection between diffusion models and diffusion processes.
डिफ्यूजन प्रोसेस है। डिफ्यूजन मॉडल का मतलब पता है क्या है? कि एक ऐसा मॉडल जिसके वजह से मतलब कि रैंडमनेस में पैटर्न आइडेंटिफाई करना, सिंपल सा जो हम कर रहे हैं, और क्या समझ रहा है? जो
अच्छा
रैंडमनेस है
अच्छा अच्छा अच्छा।
हम्म,
ठीक है ठीक है ठीक है।
मॉडल जैसे मेरा एक मॉडल है जिसका प्रोबेबिलिटी है, उसी तरह ये भी प्रोबेबिलिटी का मॉडल है, और कुछ नहीं।
ठीक है ठीक है।
Processes in physics. This connection will help us understand how these models really work in practice and give us some powerful theory for dramatically speeding up image and video generation. Finally, we'll bring
देखा, ये जो है ना, पता है क्या हो रहा है यहाँ पे? पता है क्या बोला है यहाँ पे?
हम्म
कि ड्रामेटिकली स्पीडिंग अप, मतलब कि जो ट्रेनिंग होगा ना एआई का, उसमें डिफ्यूजन प्रोसेस का कोई हाथ नहीं है, वो ट्रांसफार्मर ही कर रहा है।
हम्म।
लेकिन उस जैसे ट्रांसफार्मर अकेले करे तो बहुत टाइम लग जाएगा उसको। तो ये
अच्छा
डिफ्यूजन ट्रांसफार्मर्स प्लस डिफ्यूजन मॉडल्स का इस्तेमाल करके बहुत फास्ट ट्रेनिंग हो रहा है।
अच्छा।
बोला ना अभी कि
हाँ
फास्ट
हाँ
कर रहा है, वो डिफ्यूजन मॉडल ट्रेनिंग थोड़ी हो रहा है, फास्ट हो रहा है उससे खाली बस।
हाँ।
तो वो जो शुरू में रैंडम रैंडम पिक्सल जनरेट करता है ना, वो
हम्म
उसी में कुछ ऐसा चेंज कर रहा है ये लोग कि अपन रिजल्ट तक जल्दी पहुंच जा रहे हैं। पहले जैसे ज्यादा टाइम नहीं लगा रहा है ये जनरेट करने में।
हम्म।
बिकॉज नॉर्मल जो
तो इसमें
नॉर्मल
देख,
तो
अच्छा इसमें देख, जैसे इसमें तीनों चीज डिस्कस करेगा आगे। सबसे पहले क्लिप, तो क्लिप में मतलब इनिशियल फोटो हो गया ना।
हाँ नहीं, क्लिप तो एआई का नाम है, मॉडल का नाम है जो ओपन एआई का है।
अच्छा वो है, हाँ अच्छा ठीक है, हाँ हाँ एक्चुअली हाँ। यहाँ पे ये थर्ड वाला देख, प्रॉम्प्ट गाइडेंस।
हाँ, प्रॉम्प्ट वही तो बोल रही, प्रॉम्प्ट गाइडेंस का ही तो खेल है डिफ्यूजन मॉडल। प्रॉम्प्ट को ऐसे गाइड कर रहा है ना वो, ताकि जल्दी जल्दी से काम हो जाए, तभी तो
हाँ
मॉडल है। रैंडम थोड़ी प्रॉम्प्ट देता रहेगा, अरे रैंड समझ रहा है, ये तभी तक मॉडल है ये।
ठीक है, बड़ा आगे बढ़ा।
We'll bring these worlds together and see how approaches like CLIP are combined with diffusion models to condition and guide the generation process towards the videos we ask for in our prompts. 2020 was a landmark year for language modeling. New results in neural scaling laws and OpenAI's GPT-3 showed that bigger really was better. Massive models trained on massive datasets had capabilities that simply didn't exist in smaller models. It didn't take long for researchers to apply similar ideas to images. In February 2021, a team at OpenAI released a new model architecture called CLIP, trained on a dataset of 400 million image and caption pairs scraped from the internet. CLIP is composed of two models, one that processes text and one that processes images. The output of each of these models is a vector of length 512, and the central idea is that the vectors for a given image and its caption should be similar. To achieve this, the OpenAI team developed a clever training approach. Given a batch of image caption pairs, for example, our batch could contain a picture of a cat, a dog, and me, with the captions a photo of a cat, a photo of a dog, and a photo of a man. We then pass our 3 images into our image model and our 3 captions into our text model. We now have 3 image vectors and 3 text vectors, and we would like the vectors for the matching image caption pairs to be similar. The clever idea from here is to make use of the
समझ में आया तुम्हें क्या बोला नहीं ये वाला? ये लोग क्या कर रहा है कि 2 इनकोडर इस्तेमाल कर रहा है, ठीक है?
हम्म।
और
जो ये
एंड
ट्राई
गोल
कर रहा है ना, हाँ, एंड गोल यही है ना कि इमेज इनकोडर का जो मैट्रिक्स रहेगा और जो टेक्स्ट इनकोडर का जो मैट्रिक्स रहेगा लास्ट में सेम होना चाहिए, थोड़ा सा सिमिलर होना चाहिए।
हाँ, वो एरर कम होते जाना चाहिए।
हाँ हाँ
हाँ, तो वही बोल रहा है ना, अभी जो डिफ्यूजन मॉडल को इस्तेमाल नहीं आया, वो तो सिंपल अप्रोच है।
हाँ।
चल देते हैं।
vectors for the matching image caption pairs to be similar. The clever idea from here is to make use of the similarity not just between the corresponding images and captions, but between all image caption pairs in the batch when training our models. If we are
क्या बोला भाई?
captions, but between all image caption pairs in the batch when training our models. If we arrange our image vectors as the columns of a matrix and our text vectors as the rows, the pairs of vectors along the diagonal of our matrix correspond to matching images and captions, and all the pairs off diagonal are non-matching images and captions. The CLIP training objective seeks to maximize the similarity between corresponding image caption pairs, while simultaneously minimizing the similarity between non-corresponding image caption pairs. The C in CLIP stands for contrastive, because the model learns to contrast matching and non-matching image caption pairs. The CLIP algorithm measures similarity between vectors using a metric called cosine similarity. Geometrically, we can think of each of these vectors as pointing in some direction in high-dimensional space. Cosine similarity measures the cosine of the angle between our vectors in this space. So if our text and image vector point in the same direction, the angle between our vectors will be 0, resulting in a maximum value for our cosine similarity score of 1. So the image and text models that make up CLIP are trained to maximize the alignment of related images and captions in this shared high-dimensional space, while minimizing the alignment between unrelated images and captions. The learned
समझ में आया तुमको यहाँ पे क्या बोल रहा है ये?
geometry of this shared vector space, known as a latent or embedding space, has some really interesting properties. If I take 2 pictures of myself,
बैक करिए थोड़ा सा। इसमें यही कोशिश करेगा ना कि जो डायगोनल्स हैं, जैसे ए फोटो ऑफ कैट के सामने जो फोटो कैट का फोटो, उन दोनों के बीच में एंगल कम हो। सिमिलरली फोटो ऑफ डॉग और जो डॉग का फोटो है, उन दोनों के बीच का एंगल कम हो। अब बाकी सब का क्या हो? बाकी सब का एंगल मैक्सिमम हो।
हाँ वही, और क्या? सिमिलैरिटी मिनिमाइज कर रहा है, जो सिमिलर है उनके बीच का एंगल कम करना ट्राई कर रहा है। जो मान लो कि जो पहले से पता है कि मॉडल को ये खराब है, मतलब गलत है, उनके बीच का एंगल वो डेलिबरेटली बढ़ा रहा है हर बार हल्का हल्का।
ठीक है।
Embedding space has some really interesting properties. If I take 2 pictures of myself, one not wearing a hat and one wearing a hat, and pass both of these into our clip image model, we get two vectors in our embedding space. Now, if I take the vector corresponding to me wearing a hat and subtract the vector of me not wearing a hat, we get a new vector in our embedding space. Now, what text might this new vector correspond to? Mathematically, we took the difference of me wearing a hat and me not wearing a hat. We can search for corresponding text by passing a bunch of different words into our text encoder, and for each computing the cosine similarity between our newly computed difference vector and the text vector. Testing a set of a few hundred common words, the top ranked match with a similarity of 0.165 is the word hat, followed by cap and helmet. This is a remarkable result. The learned geometry of Clip's embedding space allows us to operate mathematically on the pure ideas or concepts in our images and text, translating the differences in the content of our images, like if there's a hat or not, into a literal distance between vectors in our embedding space.
समझ रहे हैं क्या कर रहा है ये लोग ट्रेन कर रहा है टेक्स्ट इनकोडर से इमेज इनकोडर्स को इस तरह से कि इमेज को वेक्टर में कन्वर्ट कर दिया पूरा तरह से।
हाँ, इमेज को वेक्टर में कन्वर्ट कर दिया, उसके बाद उससे रिलेटेड टेक्स्ट को दोनों के बीच में रिलेट कर रहा है।
हाँ, ये बहुत बड़े स्केल पर कर रहे हैं ये लोग ताकि
हाँ,
बहुत
बहुत
बड़ा
हाँ,
डेटाबेस बन सके।
हाँ, समझ रहा हूँ, हाँ।
ओपन एआई के पास यही तो एडवांटेज है यार कि ये लोग बहुत पहले से ये सब कर रहा है, 2020 से कर रहा है ये सब। बताओ जब तक चैट जीपीटी रिलीज नहीं हुआ था तो सही से, तब तक ये लोग
2022 में आया था, 2-3 साल
हाँ, तो
तक।
ये लोग 2021 में ये सब पे काम कर रहा है। बताओ, तो सोचो यार कितना आगे का सोच के बैठा है ओपन एआई। भाई साहब।
The OpenAI team showed that Clip could produce very impressive image classification results by simply passing an image into our image encoder and then comparing the resulting vector to a set of possible captions, one for each label that could be assigned to the image, and classifying the image with whatever label resulted in the highest cosine similarity. So techniques like Clip give us a powerful shared representation of image and text, a kind of vector space of pure ideas. However, our Clip models only go one direction. We can only map image and text to our shared embedding space. We have no way of generating images and text from our embedding vectors.
Man, that would be interesting.
क्या बोला क्या यहाँ पे?
बेसिकली हम लोग ये तो कर पा रहे हैं कि टेक्स्ट और इमेज से हम लोग कैप्शन जनरेट कर पा रहे हैं,
वेक्टर ना।
हाँ, वेक्टर। लेकिन मान लिया अगर डेटा सेट उतना बड़ा हो चुका है एलएलएम्स का, उस ब्लैक बॉक्स से हम लोग सीधा इमेज और कैप्शन दोनों जनरेट कर सकते हैं।
एक रैंडम वेक्टर लिखा जाए, उससे पता लगाया जाए कौन सा इमेज है ये।
हाँ, यही बोल रहा है ना, पीछे करके देखिए, मेरे को तो यही लग
we
रहा है।
we have no way of generating images and text for our embedding vectors.
हाँ, वही।
चल ठीक है।
2020 turned out not only to be a transformative year for language modeling. A few weeks after the GPT-3 paper came out, the team at Berkeley published a paper called Denoising Diffusion Probabilistic Models, now known as DDPM. The paper showed for the first time that it was possible to generate very high-quality images using a diffusion process, where pure noise is transformed step by step into realistic images. The core idea behind diffusion models is
तो ये नहीं कर रहे ये लोग कि पहले क्या करेगा, ये लोग नॉइज वाला इमेज डालेगा, उसको धीरे धीरे करके ट्रेन करेगा हाई क्वालिटी इमेज में बनाने के लिए। चलो ठीक है।
Pretty straightforward. We take a process where pure noise is transformed step by step into realistic images. The core idea behind diffusion models is pretty straightforward. We take a set of training images and add noise to each image step by step until the image is completely destroyed. From here, we train a neural network to reverse this process. When I first learned about diffusion models, I assumed that the models would be trained to remove noise a single step at a time. Our model would be trained to predict the image in step 1 given the noisier image in step 2, trained to predict the image in step 2 given the noisier image in step 3, and so on. When it came time to generate an image, we would pass pure noise into our model, take its output and pass it back into its input again and again, and after enough steps we would have a nice image. Now, it turns out that this naive approach to building a diffusion model really does not work well. Virtually no modern models work like this. These are the training and image generation algorithms from the Berkeley team's paper. The notation is a bit dense, but there's some key details we can pull out that will help us understand what it takes to make these models really work. The first thing that surprised me is that the team added random noise to images not just during training, but also during image generation. Algorithm 2 tells us that when generating new images, at each step, after our neural network predicts a less noisy image, we need to add random noise to this image before passing it back into our model. This added noise turns out to matter a lot in practice. If we take a popular diffusion model like Stable Diffusion 2 and use the Berkeley team's image generation approach, known as DDPM sampling, we can get some really nice images. Here's the image we get when prompting the model with this prompt, asking for a tree in the desert. Now, if we remove the line of code that adds noise at each step of the generation process, we end up with a tiny, sad, blurry tree. How is it that adding random noise while generating images leads to better quality, sharper images? The second thing that surprised me when I encountered the Berkeley team's approach was that the team wasn't training models to reverse a single step in the noise addition process. Instead, the team takes an initial clean image, which they call x0, and adds scaled random noise to the image, which they call epsilon. And from here, they train the model to predict the total noise that was added to the original image. So the team is effectively asking the model to skip all the intermediate steps and make a prediction about the original image. Intuitively, this learning task seems much more difficult to me than just learning to make a noisy image slightly less noisy. The Berkeley team's paper and approach was a landmark result.
क्या समझ में आया तुमको?
That put diffusion on the map. Why does adding random noise while generating images and training the model like this work so well? The DDPM paper draws on some fairly complex theory to arrive at these algorithms. I'll include a link to a great tutorial in the description if you want to dig deeper into the theory. Happily, it turns out that there's a different but mathematically equivalent way of understanding what diffusion models are really learning, that we can use to get a visual and intuitive sense for why the DDPM algorithms work so well. The key will be thinking of diffusion models as learning a time-varying vector field. This perspective also leads to a more general approach called flow-based models, which have become very popular recently. To see how diffusion models learn this time-varying vector field, let's temporarily simplify our learning problem. One way to think about an image is as a point in high-dimensional space, where the intensity value of each pixel controls the position of the point in each dimension. If we reduce the size of our images to only 2 pixels, we can visualize the distribution of our images by plotting the pixel intensity value of our first pixel on the x-axis of a scatter plot, and the pixel intensity of our second pixel on the y-axis. So an image with a black first pixel and a white second pixel would show up at x equals 0 and y equals 1 on our scatter plot, and an all-white image would be at 1, 1, and so on. Now, real images have a very specific structure in this high-dimensional space. Let's create some structure for our points in our lower 2-dimensional space for our diffusion model to learn. The exact structure we choose doesn't matter too much at this point. Let's start with a spiral shape like this. The core idea of diffusion models, adding more and more noise to an image and then training a neural network to reverse this process, looks really interesting from the perspective of our 2D toy data.
ये लोग क्या कर रहा है भाई? मतलब इमेज को पहले खराब कर रहा है, फिर उसी खराब इमेज को सही कर रहा है ये लोग.
इसमें मेरे को ऐसा कुछ लग रहा है कि जैसे मान ले एक सही इमेज है, पहले उसमें नॉइज ऐड कर दिए, उसके बाद मॉडल को बोल रहा है कि तू सीधा प्रिडिक्ट कर वो इमेज क्या था.
हाँ भाई,
ठीक है,
खतरनाक है.
तो इससे तो बहुत कंपटीशन बचेगा ना.
हाँ,
एक तो
मतलब
हाँ,
कि हर स्टेप पे प्रिडिक्ट करवा रहे हैं कि था क्या,
हाँ,
था क्या, था
हाँ,
क्या. फिर डायरेक्ट एकदम शुरुआत का एंड प्रिडिक्ट कर देगा डायरेक्ट ना
हाँ,
वो.
हाँ, हाँ, वही, हाँ.
अरे बाप रे बाप. मतलब इस हिसाब से एआई को सिखा तो तुम कुछ भी सकते हो,
हम्म
जो चीज सीखने लायक है।
हम्म, सही
खतरनाक।
तरीका है यार।
हो, बस कंप्यूटेशन पावर बचाने का तुमको तरीका ढूंढना पड़ेगा, सिखा तो तुम कुछ भी सकते हो।
हम्म,
तो ये कंप्यूटेशन पावर ही बचा रहा होगा डिफ्यूजन मॉडल, और क्या।
हाँ कंपटीशन पर तो बचा ही रहेगा, ज्यादा जल्दी कंक्लूजन्स पे आ रहा होगा, उसको पैटर्न्स मिल रहे होंगे, डीपर
हाँ।
पैटर्न्स मिल रहे होंगे, हाई डायमेंशनल पैटर्न मिल रहे होंगे।
हम्म।
When we add random noise to an image, we're effectively changing each pixel's value by a random amount. In our toy 2D dataset, where the coordinates of a point correspond to that image's pixel intensity values, adding random noise is equivalent to taking a step in a randomly chosen direction. As we add more and more noise to our image, our point goes on a random walk. This process is equivalent to the Brownian motion that drives diffusion processes in physics, and is where diffusion models get their name. From here, it's pretty wild to think about what we're asking our diffusion model to do. Our model will see many different random walks from various starting points in our dataset, and we're effectively asking our model to reverse the clock, removing noise from our images by learning to play these diffusion processes backwards, starting our points from random locations and recovering the original structure of our dataset. How can our model learn to reverse these random walks? If we consider the specific point at the end of this 100-step random walk, in our naive diffusion modeling approach, where we ask our model to denoise images a single step at a time, this is equivalent to giving our model the coordinates of the final 100th point in our walk, and asking our model to predict the coordinates of our point at the 99th step. Although the direction of our 100th step is chosen randomly, there will be some signal in aggregate for our model to learn from here. Given enough training points, we expect many diffusion paths to go through this neighborhood. And on average, our points will be diffusing away from our starting spiral, so our model can learn to point back towards our spiral. We can now see why the Berkeley team's training objective works so well. Instead of training the model to remove noise from images one step at a time, this would correspond to predicting the coordinates of the 99th step given the 100th. The team instead trained the model to predict the total noise added across the entire walk. On our plot, this is the vector pointing from our 100th step back to the original starting point of the walk. It turns out that we can prove that learning to predict the noise added in the final step of our walk is mathematically equivalent to learning to predict the total noise added, divided by the number of steps taken. This means that when our model learns to reverse a single step, although our training data is noisy, we expect our model to ultimately learn to point back towards x0. By instead training our model to directly predict the vector pointing back towards x0, we're significantly reducing the variance of our training examples, allowing our model to learn much more efficiently, without actually changing our underlying learning objective.
अरे क्या बोल रहा है भाई ये यहाँ पे? यही बोल रहा है कि साला इस डायरेक्ट एंड प्रिडिक्ट कर रहा है ये। हेलो।
So for each point in our space, our model learns the direction pointing back towards the original data distribution. This is also known as a score function. And the intuition here is that the score function points us towards more likely, less noisy data. Now, in practice, these learned directions depend heavily on how much noise we add to our original data. After 100 steps, most of our points are far from their starting points, so our model learns to move these points back in the general direction of our spiral. However, if we train our model on examples after only one diffusion step, we end up with a much more nuanced vector field, pointing to the fine structure of our spiral. There turns out to be a clever solution to this problem. Instead of just passing in the coordinates of our point into our model, which we'll write here as a function f, we can also pass in a time variable that corresponds to the number of steps taken in our random walk. If we set t equal to 1 at our 100th step, then t would equal 0.99 at our 99th step, and so on. Conditioning our models on time like this turns out to be essential in practice, allowing our model to learn coarse vector fields for large values of t, and very refined structures as t approaches 0. After training, we can watch the time evolution of our model. We see this really interesting behavior as t approaches 0.4. our learned vector field suddenly transitions from pointing towards the center of the spiral to pointing towards the spiral itself. It feels like a phase change. We're now in a great position to resolve the final mystery of the DDPM paper. How is it that adding random noise at each step while generating images leads to better quality, sharper images?
So you just mentioned that you want to learn Python. So do not learn Python in manual way in 2025, because learning Python in manual way will take.
Let's follow the path of a single point guided by the DDPM image generation algorithm. On our 2D dataset, generating an image is equivalent to starting at a random location and working our way back to our spiral. Starting at a randomly chosen location of x equals minus 1.6 and y equals 1.8, our model's vector field points us back towards our spiral. Following the DDPM algorithm, we take a small step in the direction returned by our model and add scaled random noise, which effectively moves our point in a random direction. We'll color the steps driven by our diffusion model in blue and our random steps in gray. Note that the scale of the random step may seem large, but following our DDPM algorithm, the size of our random steps will come down as we progress. Repeating this process for 64 steps, our particle jumps around quite a bit due to both our learned vector field changing and our random noise steps, but ultimately lands nicely on our spiral. Repeating this process for a point cloud of 256 points, our reverse diffusion process starts out looking like absolute chaos, but does converge nicely, with most points landing on our spiral. Now, what happens if we remove the noise addition steps? Running our reverse diffusion process again without the random noise step, all of our points quickly move to the center of our spiral, and then make their way towards a single inside edge of the spiral. This result can help us make sense of why we saw a sad blurry tree earlier when we removed this random noise step. Instead of capturing our full spiral distribution, as we did when we included a noise step, all of our generated points end up close to the center or average of our spiral. In the space of images, averages look blurry. Conceptually, we can imagine different parts of our spiral corresponding to different images of trees in the desert. And when we remove the random noise steps from our generation process, our generated images end up in the center or average of these images, which looks like a blurry mess. Now, note that the analogy between our toy dataset and high-dimensional image dataset breaks down a bit here. If all the points on our spiral correspond to realistic images, since our generated points do still end up landing on our 2D spiral, we would expect these generated points to still look like real images, but likely with less diversity than we would want. However, in the high-dimensional space of images, it appears that our image generation process doesn't quite make it to the manifold of realistic images, resulting in a blurry, non-realistic image. This prediction of the average is not a coincidence. It turns out that we can show mathematically that our model learns to point to the mean or average of our dataset, conditioned
यार देख रहा है क्या अभी तो तुम